Hello, welcome. We are Team Core Climate Control, Team 15. My name is Dani Nascimento, and I am the project manager. The rest of my team members are Leo Flores, who is the project administrator, Fernando Duran, who is the communication officer, Kevin Ramirez, who is the chief financial officer, and Joseph Larco, who is the safety officer.
Our client is Bay Area Rapid Transit, which is more commonly known as BART. They are headquartered in Oakland and they are a public transportation company that operates trains in the San Francisco Bay Area. There are approximately 118 million passengers which ride BART trains every year, according to 2019 statistics. Our project can be summarized in three main points. The first would be to utilize outside airflow to reduce the temperature within our client's train car. Secondly, we would like to provide a more comfortable experience for our client's passenger. And lastly, we'd like to relieve the amount of load placed on the already existing HVAC system in the train car. The constraints that we had to keep in mind for our designs. First of all, we had to have a design that was compatible with the already existing train car HVAC. It should also fit within the train car clearance area. Furthermore, it should be partially or fully compatible with the other train car types. They have train car types A, B, and C. And lastly, it must be able to handle the exterior conditions of the train car as well as the weather outside of the tunnels.
Our chosen solution, Ventilator 300, is a system of strategically designed air intakes that will be placed on top of each train car. 4 systems will be used to move the required air volume needed to the inside of the train. 2 systems will face the direction that the train is moving, and once the train meets the end of its route and runs the opposite direction, the other 2 systems will begin moving the air into the train. Designed ductwork transports the air from the intake to naturally ventilate the train cars.
The steps we took to get us this far within the projects are the following. The heat generation calculation to figure out how much heat to remove, the required airflow to figure out how much air to put into the drain car, conduit calculations to figure out the sizing and the pressure drop, filter consideration to make sure the passengers are safe, louver selection, and lastly, the material selection for the protective casing.
So for the heat generation calculations, we wanted to estimate the maximum amount of heat generated within the train car at any given hour. And the reason why we wanted to know this was because we wanted to know how much heat we might have to potentially remove from the train car at any given hour. Our calculations were based off of June temperatures for San Francisco. And the reason why we chose San Francisco as our temperature basis was because San Francisco is near Oakland, so they're pretty similar in terms of weather and temperature. For calculations, we referenced ASHRAE Handbook of Fundamentals 2013, as well as supplemental information from our clients, BART, and other sources of online research in order to make the calculations. For our required airflow calculation, our required airflow in our target space was calculated using recommended values for our space type. These recommended values are defined by ASHRAE and other online resources based on our space type. Note that while the maximum and minimum values for CFM are given on the next slide, it may be that from testing, we may find that higher numbers of minimum and maximum required CFM are actually needed to remove the amount of heat that we are anticipating. If you would turn your attention to this slide, you'll find the results of our heat generation and airflow calculations, listed under 4 separate slides. Shown in tables 1-1 through 1-3 are brief lists containing our initial design conditions, our simplified train car model dimensions, and considered sources of heat gain, in that order. If you take a closer look at table 1-3, you'll notice that our walls are listed as an estimation. The reason for this is because we could not determine what the inside material of the walls were made out of. In order to solve this issue, we based our walls' heat gains off of our windows' heat gains. If you look at table 1-4, you'll see our actual results from our heat generation and airflow calculations. If 6 p.m. DST in the middle of June, Our max cooling load turns out to be about 19 kilowatts. Our minimum and maximum air changes per hour are 5 and 7 respectively. Our minimum airflow and maximum airflow are about 450 and 650 CFM.
The steps to figure out what material to use for the protective casing follow similar steps to what was done for the project, the translation. But here it is to figure out the materials index. We can think of that as the performance of the material. The function is to provide protection for the ductwork used for the inlet. The first constraint is to have a low thermal conductivity because we want an insulated material so the ducts will not warm up due to solar gain. The second is weather resistant to withstand humidity and rain. Third, environmentally safe. The first constraint equation is the stiffness of a beam that is under uniform loading because it will closely mimic the appearance of compressive forces that the inlet will endure by the wind as the train car is moving from station to station. The second moment is taken account for a hollow square because it will minimize the efficiency based on the cross-sectional area. The objective is to minimize the mass and minimize the casing of the wall. The objective equation is seen below. Using those two equations, we found the material indices on the right-hand side that will help us determine what candidate to use for our casing. And to maximize the performance, you take the inverses of those two equations. By using CES EduPack, a material database software, we were able to figure out 3 candidate materials that fit our constraints: titanium, stainless steel, and nickel chromium. Out of these 3 choices, the final selection was stainless steel because of its higher strength value compared to titanium, its lower density compared to nickel chromium, and the lowest cost compared to them both.
Inlet dimensions were considered in relation to the size of the selected louver. Since we were aiming to implement a design that allows for the maximum required airflow, each inlet will introduce half of the airflow needed to reach 650 CFM. The damper feature present on the louver allows for the introduction of air at a controlled rate in accordance to the required airflow. A vacuum static pressure ensures that the airflow is continuously being introduced. Pressure differentials that occur as a result of air velocity at the point of entrance, at the louver, friction losses from duct length, and bend allow for the movement of the required flow rate into the train car.
For our diffusers, in order to distribute our passive air evenly throughout the train car, we will incorporate 4 different intake systems, each with their own diffusers. This is to better evenly distribute our airflow throughout the train car and account for only 2 of the intakes operating when the train travels in one direction. These diffusers would be circular with a radius of 10 inches.
The ASHRAE handbook covered all aspects of required HVAC considerations, including the implementation of an efficient air filter. The air filter is an essential component that ensures the health of BART riders by making sure that the air they breathe is clean of any pollutants and debris from outside conditions. Air filters are rated at different grades to meet different application specifications. Ratings are based on the minimum efficiency reporting value and are normally from a scale of 1 to 16. With higher grades usually for hospital applications at 17 to 20 MeV. Certain factors that we had to consider for choosing a specific air filter included the type and size of particle to be removed, the pressure drop created by the filter, and its service life. The image to the right is from 2013's ASHRAE handbook, and it shows common pollutants as well as their associated particle diameters in micrometers. We found that the appropriate air filter for our application would be the Filtret 1900, which has a MERV rating of 13 due to its significant efficiency in removing as much as 90% of small particles as small as 1 micrometer. The pressure drop associated with this specific air filter is about 0.035 inches of water column, or 8.72 pascals at a CFM of 225, and 0.047 inches of water column, or 11.7 pascals for 325 CFM. The manufacturer recommends replacing this filter every 3 months, but it may be more frequent within our application as it could possibly restrict airflow. The image to the right is ASHRAE's air filter application guidelines that show the MERV ratings and the corresponding efficiency of removing particles of different diameters. This graph demonstrates the Filtret 1900's performance when compared to other similar filters. It is shown as 1 in blue. Its pressure drop is tested in inches of water column at different volumetric flow rates in terms of CFM, and we're able to see that it restricts less airflow when compared to its counterparts. The selected loaver that we decided would best fit our system is this loaver, known as the EACA 601, designed and created by Greeneck. This is a combination loaver which has a built-in damper that sits behind the loaver's stationary blades. The loaver has been tested for its performance and is certified by the Air Movement and Control Association, also known as AMCA, after having been tested through its certified ratings program. It contains drainable blades made of 6063 T5 aluminum, oriented at 45 degrees. The specific chosen dimensions are 16 inches in height by 12 inches in width and 6 inches in depth. The free area associated with these dimensions is 0.2 feet squared, or 28.8 inches squared. The pressure drop created by the loaver's free area velocity when the train is traveling at its cruising speed is found to be about 75 pascals. The beginning point of water penetration is at 1,221 feet per minute. These two images further demonstrate the EACA 601's performance. The image to the left shows the free areas in squared feet associated with different loaver dimensions, and the image to the right depicts the airflow resistance or static pressure drop at different free area velocities. We can see that our free area velocity, which we found to be about 8.5 meters per second, creates a static pressure drop of about 75 pascals.
Before we present the results of our economic analysis, we would first like to briefly mention a few comments about the analysis itself. The first two comments being that our economic analysis only considers products which our team felt would be necessary to either construct or help regulate our design system, and that all calculations are calculated per train car. These two things were done in order to simplify the calculations being made and to provide better accuracy. Another comment to mention is that our anticipated system design lifetime is considered to be 15 years for calculation purposes. And we felt that 15 years was a good enough approximation because the typical HVAC system lasts about 15 to 20 years before any real problems arise, typically. It's also important to note that all calculations shown will be in terms of present-day dollars, not regular dollars. On this slide, you'll find the results of our economic analysis. On table 2-1, as previously mentioned, here are all the products which we considered would most likely be needed to construct and regulate our system. And you can see at the bottom the sum of the costs before and after taxes. On table 2-2, we have a yearly breakdown of the total cost per year in present dollars. And if you sum up all of the costs per year for 15 years, you'll find that the net present worth of the project is approximately $7,753.33 for the entire project per train car.
The use of our design is meant solely for the movement of air into the train. Also, given that our design does not require any moving parts that produce emissions of any kind, we can confidently state that this design does not directly emit any greenhouse gases. We considered the design to have a relatively low overall environmental impact. However, appropriate life cycle assessment analyses can be performed to determine cradle-to-grave emissions once a manufacturer is established.
Due to the complexity of our project, the time constraint, and the unexpected pandemic that occurred, we weren't able to accomplish much of what we wanted to. And the following includes to run simulation to reduce turbulent flow within the air ducts, and to figure out optimal spacing/locations for the 4 inlets on top of the train car, to calculate stresses that would be used for the bolts or the screws to secure the ventilator 300, and lastly to CAD the louver, the filter, and the diffusers to show our entire system. That concludes our presentation. Thank you so much for watching and have a wonderful day.